Practice is good. Let's keep going. If you need to take a break, by all means do so. But come back and we'll finish this up here with one last problem. Find the electric field due to a finite, uniformly charged rod of length L lying on its side at some distance d away from the end of the rod. So uniformly charged rod, we're some distance from it. Let's find the electric field here. And again, by symmetry arguments, it looks like we're only going to need the x component. So we'll do the same thing. Let's take and break this up. Let's call this little piece of it delta q enclosed there. We'll define some x distance. It's the distance from P to our delta q. There's our x. And this delta q is going to be equal to some linear charge density times whatever that little piece of x is, delta x. Or we could say that the differential of q, that tiny little piece of charge enclosed, is the linear charge density times dx. Where lambda, of course, linear charge density is q over straightforward L. So the electric field due to this little tiny I bit of charge in the x direction is 1 over 4 pi epsilon naught delta q over our distance squared. And with that, I think we're set to start doing our math. Electric field due to that little bit I in the x direction is 1 over 4 pi epsilon naught delta q over x squared, which implies then that the total electric field in the x direction will be the integral of 1 over 4 pi epsilon naught, our dq over x squared, which we already said dq is lambda dx. So we could write that as pulling 1 over 4 pi epsilon naught out of the integral sign, integral of lambda dx over x squared. Where our limits of integration, we're going to integrate from x equals that distance d to x equals d plus L to get us that total length of our line of charge. This implies then that the electric field in the x direction is lambda over 4 pi epsilon naught. Our lambda can come out as well. It's a constant. Integral from d to d plus L of x squared, x to the negative 2 dx, excuse me, which is lambda over 4 pi epsilon naught times negative 1 over x from d to d plus L, which is lambda over 4 pi epsilon naught. Substituting in, we have negative 1 over d plus L minus negative 1 over d, which implies then that the electric field in the x direction is lambda over 4 pi epsilon naught. And doing a bit of rearranging here, putting a common denominator d times d plus L, we end up with, well, let's write that down here first, d times d plus L. We end up with a d, negative d plus a d plus an L, a little bit easier to deal with, which is lambda over 4 pi epsilon naught. Negative d plus d is going to be 0. That's just going to leave us an L over d times d plus L. But we also have said, again, that lambda equals q over L. So that's going to be equal to, when we replace lambda with q over L, we've still got our 4 pi epsilon naught down here times L over d times d plus L. L in the bottom, L in the top, make a ratio of 1. Electric field in the x direction is 1 over 4 pi epsilon naught times, we still have a q over d times d plus L. All right. That looks like enough practice problems for now. Please take your time. If you need to do these again, go back, practice them. See if you can't do them on your own, or see how far you can get. Then check the video again. Pause and rewind are wonderful things. Thank you so much for watching Educator.com. We'll see you in the next lesson when we talk about Gauss's law. Thanks, and make it a great day.